Anyway, so today we're going to talk about something completely different from what we've done so far, which is basically electronics. So who never did any sort of electronics here in the class? Okay, you all have like some basics. Okay, so just to be sure, I'm gonna like do a very quick overview of the kind of skills in electronics that you're potentially gonna need for 250A. You'll see that there's really nothing very complicated that we're gonna use. But you know, like this is just to sort of prevent any issue that you guys might have, you know, and so that you have like a basic understanding of how this works. So I'm already kind of anticipating what we're going to do in lab 3. Okay, so you know, lab 1 was due today. Lab 2 is going to be due in a week. Okay. I haven't really talked about this, but I'll talk about it like later today. So this is lab 3, so now we're already like looking ahead in 2 weeks, basically. Okay. Cool. So in lab 3, there's a link to this webpage. This webpage is on the CCRMA wiki, and it's kind of old now. It's Ed Bertle wrote this webpage. We'll talk more about Ed Bertle later during the quarter because he contributed a lot to this field. Hello. He contributed a lot to this field, and he did a lot of things with haptics and physical interaction design in general. And actually, he used to be the instructor for this class before the previous instructor for this class. You know, like so. So basically, when I took 250A, he was the instructor. So Ed put together this sort of nice resource. You know, I mean, I'm sure you can find probably something better somewhere else. You know, like, but to me, like for what we do in 250A, this is fairly well adapted, and it actually just works. Okay, so this is sort of metaphor for an electronic circuit, and I just want to remind you very briefly about this, you know, like just to be sure that we're all on the same page. So an electronic circuit is basically a closed loop. Okay, so you know, one way to see it is basically a bucket with water, so that's the ground. Okay, and then you have a pipe. And the pipe basically plugs the bucket to the bucket. Okay, so you have water, then you have a pipe. Okay, and in this pipe you're going to have a pump. Okay, and the pump is basically going to suck the water from the pipe, and it's just going to like circulate water in the pipe, you know, back to the bucket. Okay. So an electronic circuit is exactly the same thing, at least from a metaphorical standpoint, and it's the same thing but with electrons. Okay, so instead of having water circulating in the pipe, you have like electrons. Okay, so in this model here, so in the case of the pipe with the bucket, there are sort of two parameters that are characterizing the system. One of the parameter is basically going to be the amount of water that's circulating in the pipe, okay? And then you're going to have another parameter, which is the pressure, okay? So those two parameters are connected, okay? And there's exactly the same idea for an electronic circuit, that you have like the amount of electron that's circulating in the wire and the pressure. Okay, so do you know what the pressure parameter is going to be for an electronic circuit? What characterizes pressure? Yeah,
would it be the voltage?
It's going to be the voltage, exactly. Okay, so so the higher the voltage, the more pressure you're going to have in your pipe/wire. Okay, And then what's going to characterize the amount of electrons that's circulating in the pipe / wire? The current, exactly. And so voltage is going to be valued in volts, and current is going to be valued in amps. Okay. So for the TNZ, we're always going to work with very low voltage and very low current. Okay. In fact, the voltage of the TNZ, you should already know about it at this point, is 3.3 volts. This is much lower than the voltage you have on the power plugs in this room, which is 120. Well, changes a little bit, you know, but yeah, 20. So 110, and then the current that we're going to use is always going to be fairly low, you know, because if you look at the TNZ pinout card, it actually says that the 3.3 volt pin can only give you up to 250 milliamps, which is very, very, very low. Okay, 250 milliamps, you can basically probably power, I don't know, like 8 LEDs, 10 LEDs, or something like this, you know, which is not a lot. Okay, so it means that with the TNZ, you're never going to be able to power something big. Okay, that's something you should keep in mind. If you want to power something big, you need an external power supply. And the external power supply is not going to send energy through the TNZ, because otherwise it would completely destroy it. Okay, so it means that in many cases, you're going to need to have an external power supply that brings power to the system outside of the TNZ, like not going through the TNZ. Okay, we'll talk more about this, you know, and I'm sure that some of you for their final projects might actually need that, you know, like, but some of you probably won't, you know, like, but we'll talk more about this. Okay, so one thing you have to understand here, which is very important, you know, is that in your electronic circuit there is always like a positive pin, so that's where power is going in the circuit, and then there's always the ground, which is where power is going out. Okay, so I know that what I'm saying here might seem extremely basic, you know, but like many things in this class, the reason why we're talking about this is because I know from experience that people tend to forget about that kind of things. And so one of the main source of problems you might have in your electronic circuit in 250A is that either power is not plugged or ground is not plugged, you know. And if one of them is not plugged, then it's just not going to work. So anyway, this is just very basic stuff, you know, like, but I thought it was kind of important to remind you about. Okay, so now back to this super simple diagram. Here we have a resistor, okay, and if we think about this view, like metaphorical view of the pipe with the bucket, what would be the equivalent to a resistor in a pipe?
Like the width?
Yeah, exactly. It's going to be the width of the pipe. Okay, so basically one way to put a resistor in this circuit would be just to put like some kind of, I don't know, some kind of washer or something like this in the pipe that would basically diminish the diameter of the pipe. Okay, so that's one big difference between the pipe and the water and the electronic circuit and the electrons. In this scenario, it doesn't matter if you don't put a resistor, because, you know, water is going to go through the pipe, and as long as the pipe is, I don't know, like resistant enough, the pipe is not going to blow up, you know, and there's not going to be water everywhere. Okay. With the electronic circuit, you need to Anyway, so I'm here. Okay. Do you have any questions about this? Or the reason why I'm showing you this is because in many cases you're actually going to need different voltages than the one that's provided by the teensy, you know, and potentially this is a way to get a lower voltage than the voltage you're going to get from the teensy. Okay. You have any questions? No? Okay. So we're gonna try to sort of implement this by putting together like super basic circuit using some of the elements that we have in the kit. Cool. So I'm gonna switch to the camera. Cool. All right, so to do this, we're going to need the breadboard. So I know some of you said they never used the breadboard, so I'm just going to give you like a very brief reminder of how breadboards are actually wired. So on a breadboard, there are two different kinds of connections. You have wires that are connected like this, okay? So it means that all the pins that are on this blue line are connected together, okay? So this is connected to this is connected to this, you know, like this is connected to this, you know, like all those pins are wired together, okay? And then it's exactly the same thing for the positive line, which is the red line here. All these pins are connected together. Okay, so the reason for this is because in most cases, the thing that you need the most when you build an electronic circuit is power, okay? So it means that those two lines are going to be used to bring power to your circuit. Okay, so this is the teensy. Can someone tell me where, for example, this blue line here is going to be connected on the teensy? Ground. It's going to be connected to the ground. Okay, so it means that we need to figure out where the ground is on the teensy. Okay, so that's the pinout card of the teensy. You can actually get the ground in two different locations. One is here and one is here. Okay, you choose. They're the same. I'm going to get this one. You want to be, again, extremely careful about VIN, which should never be used if you don't know what you're doing with it, because you could really destroy the teensy. Again, if you plug VIN to any other pin on the teensy, you will probably burn it. So don't do it. Cool. So I'm going to take the ground wire and I'm going to bring it to the teensy, and I'm going to bring it to the second pin like this, okay? And so now the ground is connected to the breadboard, okay? So then I'm going to do the same thing for power. So the positive pin here is going to be connected where on the teensy? Well, it's going to be connected to 3.3 volts, okay? Because this is the power supply of the teensy. Again, your whole electronic circuit you're going to put together on the breadboard is going to be powered at 3.3 volts, because that's what the teensy expects, okay? So it means that now I'm just going to connect the plus line, so this one here, to 3.3 volts on the teensy, okay? Does that make sense? Cool. So if you're putting together a large circuit, you might need more than the pins that are only available on this side, you know, and like this red line for plus and this blue line for minus is not connected to this plus line and to this minus line. So if you want to have power on both sides of your breadboard, you actually have to take power here and then bring it here, okay? And then you have to do the same thing for minus. So minus, do this, and then do that, okay? So now there's power on both sides, which is naturally going to be very useful for what we do today, you know, like, it was just like to tell you about this. Okay, cool. So I'm actually going to remove those wires. So the next thing we're going to do now is we're going to try to plug a sensor to the TNZ. And the sensor we're going to plug to the TNZ is going to be a potentiometer. Okay, so a potentiometer is basically an adjustable resistor, and the ones that are provided in your kit are, well, I think it really depends on what kit you have, because this is very, very random. Okay, it is very random. So this one is 10K, this one is 20K, and this one is 5K. It's very likely that it's not your case. Okay, so it doesn't really matter because the way we're going to use the potentiometer in this circuit is not as a resistor, but is as a way to provide more or less current to the TNZ. Okay, so depending on how you wire the potentiometer, it can either act as an adjustable resistor or as something that's going to provide more or less current. Okay. This is what we're going to do now. Like, we're going to wire the potentiometer so that it provides more or less current, so that we can measure the amount of current provided by the potentiometer with the TNZ to control potentially sound synthesis parameters. Okay, cool. So to do this, you see there's 3 different pins on the potentiometer, like this one, and this one. Okay, so to wire the potentiometer so that it provides more or less current, we're going to have to bring ground to one of the pins at the extremity. So it doesn't matter if you choose this one or this one, okay? And then for the other pin on one of the extremities, you're going to bring power. Okay. So basically, now we're not going to wire the middle pin. We're only going to wire like the left and the right pin. It doesn't matter if you bring power or ground to one or the other. It's just going to reverse the orientation of your potentiometer, basically. Okay. So that's potentially something that you can adjust afterwards. Okay. So how is this going to work? So those potentiometers can potentially be put on the breadboard, but it's not necessarily very practical. But for now, for prototyping, that's what you guys are going to have to do for lab 3. Okay, so it's kind of flimsy a little bit, you know, like those, it doesn't really fit very well in the breadboard, but it does work, you know, like, so potentially you might have like to hold it a little bit, you know. Okay, so for the breadboard, so far we talked about the lines that are on the extremities of the breadboard. We haven't talked about these lines, okay? So the lines that are at the center of the breadboard are wired in the other direction, okay? So where these lines are wired in this direction here, these lines are actually wired like this, okay? So this pin is connected to this pin, is connected to this pin, is connected to this pin, which is connected to this pin, okay? And they're not connected on both sides, okay? So this is another set of pin. So this pin here is not connected to this one, okay? So those 5 pins here are connected together, and those 5 pins here are connected together. Okay, so I'm gonna take a potentiometer and I'm just gonna stab it you know, it's just not possible to work with this thing. Okay, so you have any questions so far, or no? Cool. So back to what we were doing. So we know now that A0 is available. So what we're going to do is we're going to use a jumper wire to connect the middle pin of the potentiometer. So this guy, we're going to connect it to A0, which is basically this pin here. Okay, does that make sense? Cool. So now that this is done, I'm going to connect the Teensy to my computer, and we're going to verify that this is actually working. So I'm gonna connect this to this. Okay, so I'll take that for now. All right, so there is an important rule, which is that whatever you do on the breadboard, you do it when the Teensy is not plugged to your computer. Okay? Because you know there is current in the Teensy. Potentially, you could, you know, if you don't do the right thing, you could actually fry your circuit. You know, and you're probably not going to fry your computer. Probably. But you could fry the Teensy though. Okay, so I'm gonna start the Teensy Duino program. From now I'm gonna put this here. Okay. Cool. So I'm going to print in the debugger the values that we're getting from the potentiometer. So to do this, I'm going to initialize serial. So I'm going to say serial begin, 9,600. Okay, and then what I'm going to do is I'm going to print the values that I'm getting from analog read. Okay, and here I need to specify the pin that I want to read with analog read, and this pin is going to be A0. Okay, so you get it. I'm just going to read the value from analog pin A0, and I'm going to print it in the debugger. For this to work, I need to put a delay. If I don't put the delay, then there's a chance that I send too much data to my USB bus, which would be a problem. Okay, so now I'm going to upload this to the Teensy. And okay, sometimes the Teensy needs a little help for the upload. Okay, and so now I'm gonna open. So if the serial monitor doesn't want to open, you want to go in Tools, and then you want to go in Port. And in Port, you want to select the Teensy, and then it should actually display something. Okay, so the values that I'm getting here are not values in volts. Okay. Like the Teensy currently is not outputting 520 volts, you know. If it was the case, I would probably die touching it. And so you see that if I increase the value of the potentiometer, it's increasing the value on the debugger. And if I decrease the value of the potentiometer, now I'm back to 0, okay? So you see that the values that we're getting are between 0 and 1023. So why is that? Why am I not getting a voltage? So why 1023? Yeah.
Oh, I think it's like 2 to the 10 minus 1 or something like that.
Exactly. Yeah. So it's just that so basically the analog pins of the TNZ are connected to what we call an ADC. You know, an analog to digital converter. And ADCs have more or less resolution. Turns out that the one on the TNZ has 10 bits of resolution. Okay. And 10 bits of resolution is basically, as you said, nothing's working here. You know, like it's Thank you. Cool. So basically, if you want to know how many values you can actually express with 10 bits, you know, it's 2 to the power of 10, okay? And 2 to the power of 10 is 1024, and so here we have 1023 because we start from 0, okay? So that's why we have this value. So basically, the TNZ doesn't measure a voltage, it measures a value on 10 bits, okay? You could probably convert it to a voltage if you wanted to, you know, like, because this is linear, so you can fairly assume that 1023 is 3.3 volts, you know, and then it's just a matter of doing like a rule of thumb, you know, like to sort of compute the voltage based on this. But in practice, you're never really going to need to know the voltage, you know, like so as long as you know what the max is and what the minimum is, you know, like you're basically fine. Okay. Cool. Any questions about this or no? All right, so now we're going to try to plug this to what we did on Monday. So you remember on Monday we synthesized some sound in TNZ. And so here what we're going to try to do is to control some sound synthesis parameters using the values that we're getting here from the potentiometer. Okay, so I'm just going to reuse this example. So this is the example from Monday, okay? And just as a quick reminder, so on Monday we implemented a sawtooth wave oscillator, and the sawtooth wave oscillator had a frequency control, and the frequency was controlled by random numbers between 100 and 2000 every 100 milliseconds, okay? So here, instead of doing this, what I'm going to do is I'm going to want to control the frequency using the potentiometer. So could I just do this like analog read A0? Okay, would that work? Well, yes and no. Yes, it might kind of work, you know, like, but there is a little issue if I do this. What is the issue? Okay, what is the range of analog read right now? 0 to 1023. Is 0 a good frequency? No. So that's kind of a rule in audio DSP, like you never really want to use 0 for anything, you know, like, and especially not to configure an oscillator. Because the problem of 0 is a very dangerous number. Why is it a very dangerous number? Well, who knows, like if you do a division by 0 with something, you never know what's going to happen, I was talking to Mark yesterday, who's a PhD student here, and he was like, a student blew up a speaker like this by doing a division by 0, and so like yesterday, and so like you don't want to do divisions by 0, like so to not have this kind of problem, you never really want to use 0. And in any case, like a valid frequency is not 0 hertz, like I mean a valid frequency is a number like from 20 hertz, basically, right? Okay, so so it means that I need to do some scaling on this to make sure that it's not gonna start. All right, so a dirty fix to this. Is just to at least add some value to this for now. Okay, so I'm gonna do this in a somewhat clean way by saying that I'm declaring frequency. Okay, so this is my frequency parameter, and I'm gonna say that frequency is equal to analog read. And we are reading a 0, okay? And so I'm just gonna add for now like 50 to this, okay? So now I have a value which starts at 50 and that goes to 1073, okay? Cool. So I'm going to upload this on the Teensy.
Don't forget to change in the next line.
Oh, yeah, thank you. You don't want to do the division by 0. Yeah, thank you. Okay. You probably saved us all, like. Okay, good point. All right, so I'm now going to connect this to the Teensy. There is no sound. Oh yeah. Wait. No. Well, it's supposed to make sound. So you're gonna have this problem a lot in this class, right? Like the problem of there's no sound. Now, why is there no sound? I wonder if. You know what's very scary about the no sound problem is that you know that when it's going to start playing, it might be super loud, you know? So, but, dude, are you afraid now?
I like shockers. It's like I'm gonna be familiar with everything.
Okay, let me try to put it back to what it was before. So I was on random, yeah, I was on random between whatever. That's funny because this program was working on Monday, right? So what did I change potentially that could have broken this? Okay, well, is it printing something? Oh, this program is the broken program from Monday. But you remember, like at the end of the class on Monday, I purposely tried to break the TD, you know, and so so this program is basically the one that's not working. So sorry about this. So I actually need to have a functional program, and okay, where? So this is my Arduino folder. This is the 258 program, and I think the functional one should still be in my downloads. Okay, so I'm gonna drag and drop first sawtooth in here, overwrite, upload. Okay, careful, it might be loud, Okay, good. So, much better. So here I'm gonna plug freak. And okay, now I should be able to control the frequency using the potentiometer. So you hear that there are steps. So you know, it's like, and so this is because, I'm sorry, I have no way to turn down the volume. So we're just gonna do the rest of the class like this. Okay? What about this? So I'm gonna comment out the serial line here, and I can actually get rid of the delay completely now. You know, like the delay is only here so that I don't completely bomb the USB bus with information. Here, if I don't send anything, I don't need the delay. Okay, now there's no more steps. Cool. Do you have any questions about this? So basically, once you know this, you know everything. No, but actually, you know, like, I mean, if you understood everything that we've done in 258 up to now, like, you have enough information to actually build something. You know, like, you can make sound, on the Teamsy, and you can actually control what you're doing. You know, like, and so with all these information at this point, you know enough to actually do something that's potentially interesting. Okay. You don't seem to agree, but well, it will only be interesting if you're good enough to make it interesting. Okay. Cool. So adding more potentiometers is super straightforward. You know, because basically all you have to do is just to copy and paste these two lines. You know, like you could have another potentiometer to control the gain, and then every time it's just a matter of mapping the values that you're getting from A0 so that it has the range that you want to control the value that you need. So there is, this is kind of a brute force way of doing this, you know, like there is actually a map function that you can use on the Teensy if you want to map some values that have a certain range to a different range. But you know, like, I mean, just doing this mathematically speaking with one multiplication and one addition is completely fine as well. So yeah. Cool. So one thing that I want to say here, again, about the delay. So here I got rid of the delay because I'm not printing anything. If you're printing something, you need the delay. If you're not printing anything, you don't need the delay. One thing that's super cool about the Teensy and the fact that we can do this is that this is almost a system with no latency. If you were to turn the Teensy into a MIDI controller, which is something that you can do, and maybe I can tell you very quickly about this before we move on to the next step. But if you were to turn the Teensy into a MIDI controller that's connected to your computer and you're controlling something with the Teensy on your computer, you're going to have some latency, okay? Here, because the Teensy doesn't have an operating system, it's a system that runs completely bare metal. The latency you get here is probably like inferior to 1 millisecond, which is much lower than any latency you're going to be able to get on your computer. You know, another cool thing about the Teensy compared to your computer is that it just starts whenever you plug it. You know, if you were to use a Raspberry Pi or if you were to use a BeagleBone or something like this, you have to wait for the operating system to start. You know, for instance, for Linux to start. And here there is no operating system, so whenever you plug the Teensy, it just starts making sound, you know, and this is actually a fairly big advantage. So since we're talking about latency, in musical interfaces, so again, you know, like the latency is the time it takes to press a key or do something, like have some kind of action, and the effect it's going to have on the sound that is being produced, okay? So on this instrument, there is no latency, or maybe just a little bit, you know, because maybe the hammer has a little bit of latency, you know, like, but pretty much when I press the key, a sound is produced, okay? On your computer, there is a bit of latency because of all the things that we talked about. So for digital musical instruments, do you sort of have an idea of what a reasonable latency is? Yeah.
Would it be like less than 50 milliseconds or?
15 or 50?
Like 50, like you can't hear the difference between 50 milliseconds. So it would be like less than like 5 milliseconds.
Yeah, like it really depends. So the accepted number in this community is that an unperceivable latency is a latency inferior to 10 milliseconds. Okay, if it's more than 10 milliseconds, depending on what instrument you're playing, you might actually perceive it. Okay, there were studies on this, you know, like people wrote papers, you know, and like the number is 10 millisecond, okay? So below 10 millisecond, you're not supposed to be able like to tell, and if you're above 10 millisecond, depending on what instrument you're playing, you might be able to tell. That being said, this also depends a lot on what you're doing, you know, and so if you're playing the piano, for example, 10 millisecond is probably a good number, okay? Now, if you're playing a drum kit, and if you're doing like a drum roll, for example, you know, like, so you know, if you're doing a drum roll, 10 milliseconds is probably not low enough. You probably want, because you know, if you do a drum roll, you're basically striking the drum 10 to 15 times per second. And some people actually manage to go all the way up to 30 times per second, which is a lot, you know. And in order to be able to do that, your brain needs to be able like to sort of analyze what you're doing. And if latency is too low, then it's going to be really, really tough. But then there is the other extreme example. You know, like, do you know of an instrument which is an acoustic instrument, like a traditional musical instrument that has a lot of latency by nature, and that people actually just deal with it? There is one, really, just or maybe two, but. Sean? Oh, I thought you raised your...
No.
Okay.
Maybe an organ?
An organ! Like a church organ has latency. And it has latency not because the instrument itself has latency, but because the pipes of the organ are very far from the person who's actually playing. You know? So it depends on what organ you're talking about, but you know, in some churches, the pipes of the organ are distributed everywhere in the church, you know? And so the seat where the performer is on the opposite side of some of the pipes in the church. And the time it takes for sound to go from the pipe back to the performer is way more than 10 milliseconds, you know, like because of the speed of sound in the air. And so so for church organ players, not only you have latency, but the latency is different on every key, basically, depending on where the pipe is in the church. Which is why, like, usually, is there any church organ player in the room, or no? Okay, so like church organs learn how to deal with this, you know, and usually like the first thing that you learn as a church organ is not to listen to what you're doing, because if you listen to what you're doing, then you're completely screwed, basically, you know, because there is such a big difference between like what you play and what you hear that it's really, really hard to do this, you know, like, so usually church organ players, they actually listen to the sound of the keys, like the you know, and they don't listen to the sound that they actually make, because if they listen to the sound that they actually make, then they are going to have problems. Carillon also have a fair amount of latency, because if they're like huge carillons, you know, like probably the bell of the carillon, like some of the bells are very far from the seat of the performer. So the reason why I'm talking about this is because some people in this field care a lot about latency, and they're going to tell you, yeah, you know, if you have a latency which is more than 5 milliseconds or something like this, you're never going to be able to play. It's not going to be a good instrument. Well, then you can tell them about the organ, you know, and so in the end, it's a question of learning how to use your instrument, you know, and every instrument has defaults, and so it's just a matter of learning how to deal with them, right? But if you can make an instrument with low latency, it's better, though, you know? Which is something that you can do here in 258 with the tools that are provided to you. Okay. Do you have any questions on this, or? Cool. Very briefly, so if you wanted to, so if instead of making an embedded musical instrument where sound is synthesized on the Teensy, if you wanted to make a MIDI interface, so like Launchpad or whatever, you know, or like your own thing, which is something that we strongly encourage in 258, you can actually use the Teensy to make a MIDI interface, like a USB MIDI interface. And it's super, super, super straightforward. So what's probably the best resource to do this is to look at the 258 website from when? From spring 2018? No. Spring 2018 doesn't exist. Maybe it was winter. Yeah. Okay. So at the time we were using Chuck because Gap was teaching 258, and so basically, if you go in Lab 2, sensors to Chuck. So see, there was already a TeamZ, but it was a TeamZ 3.2 because the 4.0 didn't exist at the time. Okay. And so what we were doing is that we were doing exactly the same thing as what we're doing now, except that instead of synthesizing sound on the TeamZ, we were sending MIDI values with the TeamZ to Chuck. Okay? And you see that it's super, super simple. You know, like this is the whole program for this. And essentially what you do is you do analog read, then you do some mapping / scaling, then you get your MIDI value. MIDI value is a number between 0 and 127. And then we use this library, which is part of the TeamZ environment, and it's the USB MIDI library, and you just say USB MIDI send control change. And then you can give it a MIDI CC number, you can give it a MIDI value, MIDI channel, and then all you have to do is to tell your TeamZ. So if you go in Tools, if you go in Board, if you go in Tools, if you go in USB type, you can actually choose MIDI. Okay, and once you've done this, whenever you're going to plug your TeamZ to any system, it's actually going to appear as a MIDI interface. Okay, so it means that your TeamZ will not be recognized as a TeamZ anymore. It will be recognized as a MIDI interface, and that's pretty cool because, for example, if you have an iPhone and you want to control a sound synthesizer that's working on your iPhone, you can actually connect the TeamZ to your iPhone using like USB and just send MIDI messages to your iPhone. And that's cool because, you know, Apple devices are very restrictive in terms of what you can plug to them. And MIDI is kind of the only exception to this. And so for some time, for example, I don't know if you remember those, but and I'm not even sure they still exist, you know, but they were those credit card readers that you could connect to an iPhone. They were actually using MIDI to send the information from the credit card to the iPhone, because that way they didn't have to pay Apple to allow them to make a custom device that would connect to the iPhone, you know, and so MIDI is kind of the only thing that Apple tolerates to be connected without being approved by Apple to your device, you know, and so you can make a musical instrument like very quickly just by, you know, like taking a TeamZ and sending sensor values from the TeamZ to your smartphone using MIDI, you know, and so I think that's pretty cool, you know, and I'm just showing you this so that you know it's there. For 258, we prefer if you use, like if you make something which is an embedded instrument, but for your final projects, if for some reasons you wanted to make something that involves like multi-channel, for example, you know, like, say you want to make a piece and your piece needs 16 speakers in a room or something like this. You're not going to get 16 speakers out of the TeamZ, right? So if you make a point to like make an interface more than a fully embedded musical instruments for your final project, that's acceptable, okay? But you really need to make a point for this, okay? It's like, I really need to do this. I can't do it with the TeamZ and the Audio Shield, so can I make an interface, you know? And that's fine, you know? But, any questions about this? you look at the screen, you probably noticed that there is something here that says audio. So that's another cool thing that you can do with a TNZ. You can actually turn your TNZ into an external audio interface. And so then there is a specific object that you can use in the TNZ environment, which is like audio output USB or audio input USB. And then your TNZ is an audio interface, you know, and so that's very convenient, you know, because it means that it will be recognized as an audio interface by your computer, and then you will be able to use it with, I don't know, Macs or Perdata or whatever you're using, or Chuck, or you know, and so this is potentially super convenient. Okay, so just to finish on sensors for today. So the potentiometer is kind of a very simple case. It's like probably the simplest thing that you can do. But there are sensors that are slightly more complicated, and so we're gonna talk about them. Okay, so the potentiometer is easy because there are 3 pins. Okay, and there's 2 pins for power and ground, and then there is 1 pin for the output. Now, there are sensors in your kit, such as the FSR, that only have 2 pins. So how do you work with those? So that's the FSR, that's a force-sensitive resistor. So it is a resistor, just like the potentiometer, except that to control the amount of resistance that the system is giving, you press on it, okay? So, so that's like a pressure controller. So how do you interface that to your TNZ? Because again, you only have 2 pins on the FSR, right? Like this guy and this guy. Okay. So to do this, we need to make a very simple electronic circuit, which is going to look like this. So on one side, you're going to have a Vin, and Vin is basically your 3.3 volt pin, okay? And then your 3.3 volt pin is going to be connected to one of, so that's the FSR, okay? And Vn is going to be connected to one of the 2 pins. Doesn't matter which one, okay? You choose. Okay, and then the other pin is going to be connected. Do you know to what it's going to be connected to? Well, we want to measure what's going to come out of this. So, how do we measure analog things on the TNZ?
A0.
A0 or A whatever, okay? So basically, this is going to be connected to potentially A0, okay? Well, let's try. I'm already telling you this is not going to work well, but because there is no ground, okay? So then we're going to have to see how we actually deal with the ground. But basically, I'm just going to plug this guy to the breadboard, okay, and I'm gonna get power on one of the pins, okay. So now power is going to one of the 2 pins of the FSR, and then I'm gonna take the other pin. I'm going to disconnect the potentiometer, and I'm going to connect it to this like this, okay? Cool, so I will bring this back here. And I'm going to reuse our super simple program here, which is just values, uploading it on the Teensy. Okay. So now if I display the values, well, it's not really doing what I want, right? Oh, okay. Oh, sorry. So, see, it's kind of giving me something. It looks like when I'm pressing, something kind of happens, but it's not very usable, okay? So the reason for this is because I'm missing a ground, okay? And how am I going to add the ground to this? Well, it's pretty straightforward. I'm going to use what we call a pull-down resistor, okay? So I'm going to use a resistor here, which is going to be my 10K resistor, and I'm going to connect the 10K resistor to the ground, okay? So what this is going to do practically is that, well, it's going to change the resistance of the FSR, but it's also going to sort of suck all the remaining electrons in this wire if I'm not pressing on the FSR. Because the problem with analog pins on the Teensy, and that's the same for Arduinos, is that you always have electrons kind of floating in those pins. And so if you're sending a current which is very low, it's very hard to measure it because there is no ground, and so the electrons are floating. And so here with the 10K resistor, I'm sort of bringing all these floating electrons to the ground, okay? And so this is very important. There are two different ways of doing this. One is to use a pull-down resistor, which means that it's pulling current down because it's connected to the ground. Another way to do this is to use a pull-up resistor. And a pull-up resistor is going to do the opposite. It's like, it's always going to pull things up, and when you're going to press on the FSR, it's going to pull down, okay? And we're using pull-down here because they're, I don't know, in my opinion, they're a little bit easier to understand, like from a conceptual standpoint, you know, like so this basically sets the reference to 0, and when you press on the FSR, it's gonna like bring it up. Cool. So there are resistors in your kit that you can use for this, okay, and those resistors are 10K resistors, and so I'm basically just going to implement this circuit here, and okay, I'll bring it back over here so that you see what I'm doing. Okay, so this is pretty straightforward. So the red wire that I have here is the wire that's reading the value from the FSR, okay? So what I'll do is that I'll just put a resistor here, okay? See? So you can actually put a resistors directly on the breadboard, and then I will connect the other side of the resistor to the ground, just like that. Does that make sense? So it's basically what I just did here. Okay. There are cleaner pictures of this on the course website. So then, now if I replug the Teensy, 0. Nice. Okay. And so now if I press on the FSR, I can actually control the amount of current that's going into the system. Okay. Nice. And so now, if I want to have fun, I can try to run it through the other program, which is the one that actually makes sound. Okay. And, work on this kind of stuff, is that when you make sound toys, you spend a lot of time playing with them. Especially if you have problems. It's like you've been working on this thing for like 3 hours, and you don't know where the problem is, but it's really fun to play, and so you spend way more time just doing the than actually trying to fix the problem. So you're all going to be there at some point, like I'm telling you. Cool. So the FSR is just, it's so funny, like the camera just picked you up and it's zooming on your face, and it was really like zooming progressively, just like, don't look at me, look at me. There we go, look at me, not her. Okay. This is so funny. Okay, so the FSR is working in a very similar way than many other sensors. And so, for example, the photoresistor that you had in your kit, where is it? The photoresistor, which measures the amount of light in the room, works exactly the same way as the FSR, and many sensors work this way. They only have 2 pins, and in that case, you want to use a circuit which looks like this. So, for example, here, if I remove the FSR and if I plug the photoresistor instead, it should still, see? So see, the cool thing about all this is that all these things are very interchangeable, and so once you know what you're doing, it's easy, just to try different things, and to not think too much about it. Cool. Any questions about this or no? Cool. So this is for continuous analog sensors. Now there are other kinds of sensors in your kit, including buttons. Okay. So for buttons, because they are discrete, they either give you 1 or 0. You don't necessarily want to use an analog input. It doesn't really make sense. So you want to use a digital input. And so for digital inputs, things are just slightly more complicated than for analog inputs. So I just wanted to show you how this works. Okay. So here I'm gonna add a button to the circuit. See that the buttons that we gave you, they have 2 pins. Okay, so I'm just gonna put it here like this. So I'm gonna have to bring power to the button, and basically 2 pins. 2 pins is always the same circuit. It's always this. You need a pull-down resistor for a button. Okay, and so on one side, I'm going to bring power. I'm going to need another pull-down resistor. And this other pull-down resistor is going to connect the other pin here to the ground. Okay. And then I'm going to bring the other side of this pin, which is now connected to the ground, to a digital input. So for digital inputs, it's the same as for analog inputs. I need to check which pin is available. Okay, so on this side, all the pins are digital inputs. So I'm just going to connect to 0. okay, because 0 is available. You cannot use 6, 7, 8, 10, 11, 12. Okay. So here I'm going to connect to 0, and so 0 is basically this one here on the other side. Sorry, this is not super clear. I think you got it. Cool. All right, so now I'm going to bring this back to here. Nice. Okay, and then I'm going to go back to my very basic program. So for digital pins, you need to configure the pin either in input or output mode, okay? Because there is no analog output per se on the TNZ, but there are digital outputs on the TNZ. So to do this, you're just going to say pin mode, and then you're going to say that, okay, I always forget, yeah, I should have checked this. Okay, I have an example here. I forgot the order for pin mode. Okay, no, this is looking at the Chuck program, which is not really what I wanted to do. Okay, pin mode. Okay, first it's the pin number and then it's the value. Okay, so pin mode 0 is going to be input. Okay, so here I'm configuring pin number 0 as an input. Okay. Cool. And so now instead of doing an analog read, I'm going to do a digital read of 0. Cool. So I'm going to upload the program on TNZ. And then I will check that this is working. So here I have 0. Now if I press, get 1. Okay, so this is what I wanted. Cool. So how do I integrate this to my other program? Well, it's pretty straightforward. I just copy pin mode. I put it here in setup. Okay. This is already working, so now what I'm going to do is I'm going to do Faust sawtooth, and if I remember correctly, I think there was a gain parameter, so I'm just going to set the value of the gain parameter with digital read of 0. Okay, so this is the gain value, so if it's 1, it's maximum, if it's 0, there's no sound, okay? So if I didn't make a mistake, I should actually now be able to control the fact that my instrument is making sound or not. Well, that's what I like. Okay, so it's working. Nice. Any questions? This should be fairly straightforward, you know, and so once you understood the way this works for digital read and for analog read, you know how to use 60, maybe 70% of the sensors that are out there. So in lab 3, you're going to have to sort of do all of this on your side, okay? But then I also put a documentation on how to use the other sensors that are part of your kit. And this part of the lab is kind of, it's like you don't have to do it. It's more like if you want to use the sensor, if you want to play with it, you know, like, but for example, for the distance sensor, things are slightly more complicated because those sensors are digital sensors. And because they are digital sensors, it means that they are sending digital information to the TNZ. And in that case, you need to use a library. And so it means that in order to use this sensor, you're going to have to use a library. And the library is very easy to use, because you see in the code that essentially all you do is that you include the library. Then you have an object for the sensor. And apparently there are some values here which probably configures the way it's working. And then essentially the way it works, is that measure distance in centimeters, and every time you're going to call this, it's going to give you the distance in centimeters, so it's not as low tech as the options that we're using, but this is another way of dealing with this kind of sensors, okay? So many of the sensors you're going to buy potentially on the web, they're going to work like that. They're going to work with the library, and it means we're going to have to get a library, because they are more sophisticated than all these basic sensors that are basically just adjustable resistors that we've been using so far. One thing that I wanted to say about potentiometers, because I know that people tend to get very excited whenever they start making those things, and then you're going to be like, oh yeah, I want to buy more or whatever, So potentiometers, there are many, many different kinds of potentiometers, okay? So if you buy other potentiometers for your project or for your personal use or whatever, so you want to look at the resistance. The resistance is not really that important, especially the way we use those sensors, but there are two kinds of potentiometers. There are linear potentiometers and there's logarithmic potentiometers, okay? So if you buy other potentiometers, you want to make sure that you buy linear potentiometers and not logarithmic. Logarithmic potentiometers are typically used to control the volume of a sound, for example, in an analog circuit. And it would be really annoying for you if you were buying logarithmic potentiometers, because you could make the adjustment on the software side, but because the DACs that we're using are only 10 bits, you don't have a lot of precision, and so it would not really work that well in the end. So if you want to buy new potentiometers, you buy linear potentiometers. Yeah?
Does TNC 4.0 have internal pull-down resistors at pins?
Yeah, some of them, not all of them.
Can you declare them from the pin mode?
Yeah, so the thing is, if I were you, I would not trust them.
Got
I internal pull-down resistors are, I don't know, I don't really trust them in general, so you can try, and in some cases it might work, but just to be safe, if I were you, I would just use good old resistors.
Sounds good. Thanks.
But that's a good question. Okay, so I briefly want to talk about the assignment for next week. So for next week, you're going to have to do lab 2. So you're going to have to assemble your TNZs. You're going to have to do soldering. You're going to have to go to the Max Lab to do all this. And there's an assignment which is due on April 26th, which is basically next Wednesday. The goal of this assignment is to make a music box or a sound generator using Faust and the TNZ Audio Shield. The idea is to make a system that will produce sound. And it can be tonal, it can be atonal. We're not sectarian in 250A. If you want to make tonal music, you can make tonal music. No one is going to be mad at you if you make tonal music. When plugged to the sound system and a computer or USB charger. So we want you to make something that, when you plug it, whether it's your computer or a USB charger, it actually starts producing sound. So you're going to want to use Faust for this. it can be like a sound texture generator. It can be just a music box playing a tune or something like this. It's really up to you. If you want to use notes and not frequencies, you can potentially use the MIDI key to hertz function in Faust, because that way you can use MIDI key numbers instead of hertz, which is way more practical. Just look at the lab. If you don't know what we're talking about, it's all explained in the lab. Okay. So, and then as usual, you make a video of your thing and you send it to us. So we don't care too much about coding standards in 250A, but if you write clean code, we prefer than if you write extremely dirty code, okay? So the reason why I'm saying this, is that potentially here, if you want to make like a music box, you're gonna have to create potentially an array of notes, like the melody is going to be in an array, right? It's cleaner if it's in an array than if you hard code the melody in the loop and then you have a program which is like 1,000 lines long, basically, okay? Because one way to make the melody could be to do exactly what I did here in the example. It's like you play a note, the note is 440 hertz, then you wait for 1,000 millisecond, and then you stop playing it, okay? Then you wait for 100 millisecond, and then you play a new note, okay? So there is a way to automate this in a slightly nicer way, So if you don't know how to do it, it's not a problem, but if you know how to do it, if you know how to use an array in C or in C++ or just in any programming language, please do it. Because it's going to make your life easier, and eventually, when you're going to make something more advanced than this, it might actually be useful, okay? And again, the projector agrees, as usual. So any questions? This should be pretty straightforward, it's literally just, and you don't need an interface for this homework, okay? Okay, now that you know how to make the interface, it's fine if you add one, okay? So maybe you want to anticipate homework 3, which will involve making an interface, okay? But you don't have to, okay? So it means that plug it to the wall, make sound. If you want to make a basic interface using some of the elements in your kit, feel free to do it, but you don't have to for this assignment. Questions? Yeah.
So you can't put notes into an array in Faust directly. You'd have to do it.
No. Well, you could, but I don't think it's a good idea. So, but that's a very, very good question. In general, with the tool chain that we're using here, there is some overlap between Faust and Arduino. Like, there are some stuff that you could do in Faust, but you do them on the Arduino side, and vice versa. So there is always like a middle zone where you could do something in one environment or the other. Okay. So what I would strongly recommend you to do is that you only use Faust to do sound synthesis or sound processing. Anything that's related to control, whether it's generating a melody or doing stuff like this, like you do it on the Arduino side. I think it makes way, way, way more sense, and it's going to be way, way, way less of a pain for you to do it. So, so Faust is only here to generate sound or to process sound. If you want to control something, you do it with the TZ, And so for those of you who know Chuck, this is kind of the same idea. Like Chuck is very good at controlling things, and so here, like the control layer of your program is the Arduino environment, and